ever stop to think how a single Node.js process can juggle like thousands of requests all at once? It feels impossible, right? Like some kind of tech magic. But it's not magic, it's just a really, really clever journey. So today, we're going to follow one of those requests. We're going to trace its entire secret journey from the moment a user clicks all the way into the heart of the event loop and back out again. Let's get into it.
Okay, so here's the game plan. A request's journey has 5 main stops. First, we'll see how it even leaves home, how the connection gets started. Then we'll see how the operating system's kernel gives it a big welcome. After that, we dive into the main event, the Node.js event loop itself. We'll follow the response on its way back, and then finally, we'll put all the pieces together to see why this whole setup is just such a massive win.
All right, let's kick things off with part 1, the request leaves home. Now, before any data gets sent, I'm talking before a get/b or a post/API or anything, the client and the server have to do this little formal dance. They got to introduce themselves and basically agree that they're going to talk. And this all happens down at the TCP layer.
And this is where it gets kind of cool. It's this super polite 3-step conversation. Seriously, think of it like this. The client sends a SYN packet, which is basically like knocking on the door and asking, "Hey, you there? Can we chat?" The server hears the knock and replies with a SYN-ACK, which means, "Yep, I'm here. I can hear you. Can you hear me?" And finally, the client sends back one last ACK, just to say, loud and clear. Boom. Only then, after that little handshake, is the line open and ready for our actual HTTP request.
So once that handshake is done, the operating system creates what's called a socket. The best way to think of a socket is like a private doorway, or maybe a dedicated phone line just for this one conversation. And to keep track of all these different doorways, the OS gives each one a unique number, kind of like a ticket at a code check. In the tech world, we call that ticket a file descriptor.
Okay, but what happens if like 1,000 people all try to knock on the door at the exact same time? Well, they don't all get a private doorway right away. Instead, they have to get in line. Node.js has this waiting room, a backlog, and by default, it can hold about 511 of these pending connections. But if that room gets packed, if connection number 512 shows up, it basically gets a "sorry, the club is full, come back later" message and is turned away. So, our request made it through the door and is officially connected. But it doesn't just waltz right into our JavaScript code. Nope. First, it's got to get past a very powerful, very efficient bouncer, the operating system kernel.
And this right here, this is the absolute core of Node's secret sauce. In the old school, blocking world, a thread asks for some data, and then it just stops. It sits there, twiddling its thumbs, completely stuck until the data arrives. It can't do anything else. But Node.js, it's non-blocking. It asks for data, and if it's not ready yet, the OS immediately says, "Nope, not yet. Try again later." And that frees up the Node process to instantly pivot and go handle a different request. No waiting around.
So you might be wondering, if it's not just sitting there waiting, how in the world does it know when the data is ready? Well, this is the real magic, I/O multiplexing. On Linux, it's usually epoll. On macOS, it's kqueue. Think of it like an air traffic control tower for all your connections. Instead of constantly calling every single plane, every socket, and asking, "Are you ready to land yet?" Node just tells the OS, "Hey, you're the air traffic controller. Just give me a shout when any of these thousands of planes are ready to land." It is wildly efficient.
And here's exactly how that handoff works. A data packet arrives. The kernel snags it and tucks it away in a little buffer. Then, it flips a switch on that connection socket, marking it as readable. The Node.js process, which was basically just chilling, gets an instant wake-up call from the OS that says something like, "Hey, get up! Socket number 867 has data for you." See? Node only ever spins into action when there's real work to do.
Okay, the OS has done its part. It's handed off the baton. And now, finally, our request enters the inner sanctum of Node.js itself, the famous event loop. This is where our JavaScript code finally gets to shine.
So inside what's known as the poll phase, a few things happen. Bang, bang, bang. The loop gets that notification from the OS and immediately reads the raw data from the socket. That garbled data gets fed into Node's super-fast internal parser, LHTTP, and the very instant that parser figures out what the HTTP headers are, it triggers your code, that familiar rec-res handler function that you actually wrote.
Now listen up, because this is probably the single most important thing to understand about Node. That handler function you write, the one with your logic, it runs synchronously. That means if you have a chunk of code in there that does some heavy calculation, say it takes 100 milliseconds to run and there's no await in sight, you've just blocked everything. You've caused a pileup on the single-lane highway that is the event loop. No other requests can get through until you're done.
So how do we avoid causing that massive traffic jam? Simple. Async await. This is the escape hatch. When your code hits an await for something that's going to be slow, like a database query or calling another API, it does something brilliant. It basically bookmarks its spot, hands control right back to the event loop, and says, hey, I'm going to be waiting a while for this database thing. Go ahead and work on other stuff and just ping me when my data is ready. This is the beautiful cooperative dance that lets Node handle so much at once.
Okay, so our handler did its thing. It got the data from the database, and now it's time to send the response back to the user. But this return journey has its own set of challenges, and the big one is a concept called backpressure.
Just imagine your server is a giant fire hose and the client's connection is like someone trying to drink from a tiny straw. If you just unleash the full blast, you're going to completely overwhelm them, right? Well, backpressure is the system's safety valve. When the server starts sending data way faster than the client can handle it, all the buffers start to fill up. When that happens, the res.write function will actually return false. That's a signal. It's Node screaming, whoa, hit the brakes. Your code should then pause sending data until it gets a special drain event, which is Node's way of saying, okay, the coast is clear, the client caught up, you can start the fire hose again.
Finally, with the response fully sent, it's time to hang up the phone. And just like the polite three-way handshake we used to start the call, there's a polite four-way handshake to end it. It's basically another little conversation. One side says fin for finish sending. The other says ac, acknowledging it. Then the other side says, okay, I'm finished sending too, and the first side sends a final ac. This makes sure no data gets lost in transit, and both sides agree the conversation is officially over. Clean and tidy.
So we've gone the full circle. The request left home, got processed, and the response made it back safely. But now for the big question. Why on earth do we go through all this complexity? What makes this single-threaded, event-driven model so special?
It's because this entire system was designed to solve a legendary challenge in computing known as the C10K problem. That's C for connections and 10K for 10,000. For years, it was incredibly difficult for a single server to handle 10,000 simultaneous connections. Older architectures would just fall over. But the architecture we just walked through, it was built from the ground up to crush this problem, letting a single node process juggle tens of thousands of connections without breaking a sweat.
And this chart right here just lays it all out. The traditional multi-threaded model is like hiring a separate employee for every single customer who walks into your store. It kind of works, but it's incredibly expensive. You're paying for all that memory, and you're wasting time as the manager runs around trying to check on everyone. The Node.js model, on the other hand, is like having one superhumanly efficient operator who handles every single call, instantly switching to the next person the second there's a moment of silence. It's ridiculously memory efficient, there's no time wasted switching between tasks, and it scales like crazy.
So, let's just boil it all down. The whole game is this. Node.js never blocks on I/O. Period. It offloads all the waiting to the operating system, which is built for exactly that. This keeps its one and only thread free to do what it's good at, running your JavaScript for requests that are ready to be processed right now. The end result? Super low memory usage, insane concurrency, and a perfect tool for any application that spends most of its time waiting for things like databases or other APIs, which, let's be honest, is most web apps today.
And that leaves us with one last big idea to chew on. We've just seen how unbelievably powerful this event-driven, non-blocking model is for web server. But if a single thread, when managed this cleverly, can achieve this kind of performance and scale, it makes you wonder, right? Where else could this architecture completely change the way we build software?